I just have to jump into the YouTube live stream and mute it before. So we don't have that huge echo problem as soon as it's ready to go. Okay, and it looks like it is already muted. All right, very good. July, go ahead and introduce our speaker, please.
Good evening, everyone. Alrighty, we give a welcome here to Dr. Shenoy. Am I saying that correctly?
Yes, you are. Thank you.
Shenoy. And first name, Sachin or Sachin?
Sachin.
Sachin. Okay, welcome, Dr. Sachin Shenoy. Using the 106-inch reflecting telescope mounted inside the modified Boeing 747 known as Sofia, SOFIA, Stratospheric Observatory for Infrared Astronomy, Dr. Shenoy gathers data in the infrared portion of the electromagnetic spectrum while aboard this flying observatory. This data is used to facilitate research concerning the chemistry and physics of interstellar dust. His talk will focus on some of the most recent scientific results of his work. Born and raised in Goa, India, Dr. Shenoy received his Bachelor of Science in Physics from Goa University. While there, he joined the Association of Friends of Astronomy, AFA, an amateur astronomy group leading public education and outreach efforts. He has a double master's degree from Goa University and the University of Texas at El Paso, and received his PhD in physics, specializing in astronomy from Rensselaer Polytechnic Institute in Troy, New York. He has used ground, air, and space-based observatories to study the interstellar medium. Previously, he worked as a postdoc staff scientist at NASA's Spitzer Science Center at Caltech, was a postdoctoral fellow at NASA's Ames Research Center, ARC, and an associate scientist at the University Space Research Association's Ames Research Center in Mountain View, California. He is an avid outdoor person who enjoys hiking, camping, bird watching, and enjoys cooking food from various cuisines. Welcome, Dr. Shenoy. Thank you for being here.
Thank you so much. Let me share my screen, see if this works.
Okay, I just wanted to mention one other thing I forgot. For any of you who have questions, please type your questions into the chat window. And when Sachin is done with his presentation, we'll go back to the top and take the questions in order. Thank you.
Do you guys see my slides?
Yep, we can see him.
Yes.
Okay, perfect. Thank you so much. Thanks so much for this invitation. I really love talking about Sophia and astronomy in general to anyone who will listen to me. When July 1st said I need to talk something about Sophia for this group, I thought, oh, these guys are all astronomers, so I'm just going to do a lot of basically a science talk rather than a technology talk. But then yesterday night, I got a mail from Dina saying that, oh, I'm a retired pilot and I'd love to know about 747. And I'm like, oh man, now I have to tell you all about the plane. But that's okay. We'll see how this goes. So this is a talk that I jumbled up together last night. So if there are any issues, I apologize in person. So as July said, I work at the Space Science Institute here at Boulder, but mostly support Sophia through a subcontract with USRA. And as Dina already said, what is Sophia? Sophia stands for Stratospheric Observatory for Infrared Astronomy. It's just a big 747 plane that we have taken up and modified it to become an airborne observatory. So here is a view. You will see that this is a 747, but it's not the same because there is this bulge sitting here in the back. That's where the telescope sits. This program is funded by two entities, NASA and DLR. NASA funds 80% of this project. DLR, which is our German partners, German counterparts, they support the rest 20% of things. When Sophia is flying, we can open up this door. This door is huge. It's about 15 feet by 23 feet. So, you can drive a truck through it. And inside it is our prized possession, the telescope. It's a 2-meter telescope. You can see the primary mirror here and the supporting structure in this particular image. And, many people get excited about hearing about Sophia and a telescope that's up in the plane flying at 40,000 feet. So, but Sophia is not the first one. We had other observatories, airborne observatories before Sophia. The first one was Learjet in 1968, where we took a small, tiny telescope and stuck it on the window of the plane to do astronomical observations. Then we got greedier. We wanted a bigger telescope, so we went to KAO, which stands for Kuiper Airborne Observatory, and we had a 1-meter telescope. Now it needed to have its own room in the plane. When that mission ended, we got greedier. As astronomer, we just want to go bigger, so we decided to go with a 2.5-meter telescope now in a 747. Here is an image of Kuiper Airborne Observatory, and you can see the door that is open. It's tiny compared to Sophia, and the telescope sits inside there. A few years ago, Sophia and Kuiper were both in NASA's Ames Research Center, and we had an open house where we had a few thousand people come through Sophia, take a look inside. Unfortunately, after that, we have not been able to do any open houses, mostly because of COVID and other restrictions. But after this image was taken, Kuiper was retired. Kuiper is now a museum piece in the Moffett field, and Sophia is in Dryden doing science research. Brief history of Sophia. Sophia was first acquired by Pan Am World Airways in '77. It's designated as 747 SP. For folks who know about these designation, that just means it's a special performance. It's a shorter body 747, not the classic 747 that we have from Boeing. It was christened as Clipper Lindbergh by his widow Admiral Lindbergh. It flew with Pan Am for about a decade, and then United purchased it, and they ran it for another 7-8 years. And in 1995, NASA purchased the plane. In fact, NASA purchased 2 of these planes so that when we were modifying one, the modification was done in Waco, Texas by L3 Integrated Systems. And when the plane was being modified, we had a full-size mock-up on the side, so to make sure that everything functions properly, we knew exactly where things were. After that, the first flight after the modification happened in early 2007, and then soon after, it was rededicated at NASA's Dryden Flight Research Center in Palmdale, which is about an hour from Los Angeles. In 2009, it was the first time that we opened the door. Remember, everyone has seen Hollywood movies, and as soon as there is a tiny bullet hole in the airplane explodes. And we wanted to open up a door that is 23 feet by 15 feet. So the pilots obviously were very nervous. But because of the technical improvements that were done on the plane itself, when the door is open, the pilots tell us now that they don't even notice. They just fly as if nothing is happening. The first light for forecast was in the May of 2010, where we observed Jupiter and M82. And the regular observing cycle, science operations began in 2012. That's the year I also joined Sophia. And then I've been with them from 2012 till now, doing mostly science operations. In our summer, we go to New Zealand because it's winter there, and winter observing, as you all know, is perfect, especially for infrared astronomy. So we go to New Zealand in Christchurch. So here is a cutout of Sophia. So I hope you can see my cursor. This is the main cabin. The telescope sits in the back of the plane. There is a pressure bulkhead, so the telescope is open to space, but there is a pressure bulkhead which separates folks who are sitting here, people like us who are working in the plane, from the telescope. There is an azimuth tube that comes in, and that's where all our instruments sit. And just in front of the instrument is a science operation crew station. These are the people who control the instrument, and the people on the right-hand side are the ones who control the telescopes. The mission director sits here behind the telescope operator, and people like me, scientists, sit on these tables. We also have educators on board sometimes, and they get to come with us, see how Sophia functions, look at the operations, see what kind of research we do, and they usually occupy this station. I don't have to introduce telescope to this audience, but just to make sure we are complete, we have a primary mirror where the light is collected, which is 2.5 meters. Then we have a secondary mirror, which reflects the light to a tertiary, and then it goes inside to the focal plane where our instruments is. This is how the engineering diagram looks. Here is the 2.5 meter mirror with its supports, and the green thing is the pressure bulkhead. When you're inside Sophia, this is how it looks like. So it's pretty big. You can see that the tube is as big as the plane itself. For comparison, there is a person standing right next to the telescope. This view shows just the telescope tube coming into the plane. There is no instrument mounted, but when we mount the instrument, this is where the instrument goes. These black things that you are seeing are the pressure dampers. So when there is large turbulences, these are pressure valves that hold the telescope in place and doesn't allow it to move. This whole the blue round thing you're seeing is a bearing, which when we fly up to 10,000 feet, we flood the bearing with oil so that the entire telescope, this 20-ton telescope, gets lifted and it is separate from the body of the plane, which means no matter what the plane does, the telescope is focused on one star or looking at one star. So when you're sitting inside the plane, when you're looking at the back of the plane, it feels as if the telescope is moving all over. And you'd question, how is it possible to do any observation when the telescope is moving so much? But we need to realize that the telescope is in an inertial system, which means it's not the telescope that is moving. It's actually the plane that is moving around us. So no matter what the plane does, the telescope is always pointing towards the object that we are observing. We also have 3 gyroscopes, which tracks the star and keeps the telescope pointed in the right direction. Okay. So here is a typical flight path that we take. We start in Palmdale, California, and we can fly anywhere in continental US, or we can go up to Canada or over the ocean. And depending on, remember the telescope is looking on one side of the plane. So if we want to observe something that's in a different part of the sky, we have to move the plane around. So that's what you're noticing. That's what you're seeing in this animation. Like every time we have to observe something different, the plane moves around, we do our observation, and then we land back next day morning. On the plot here, what you're seeing is the altitude of the plane. So initially we start at 0, then we fly up to about 39,000 feet and start observing. And you'll notice that as the night passes, we go higher and higher. And that's just because when we first start, the plane is pretty heavy because we take a full load of fuel. So as we fly, we exhaust the fuel and the plane gets lighter. So it's easier to take up. So we start about at 39,000 feet and end up at about 43,000 feet by the end of the night. And in the inset here shows instrument forecast that's been attached to the telescope. Here is a year's worth of Sophia travels. This was from a few years ago, from 2015. And you'll see that we fly all over the place, all over US, Canada, or on the ocean. You'll notice that we don't go into Mexico. And that's because the Mexican whatever the Air Force authority is, doesn't allow us to fly over Mexico. So we can't do any of the observation by going to Mexico. We have to do it in US or up in Canada. You'll also notice that there is one flight path that goes and ends up in Hawaii. It's not that we were on vacation there. It was just that we were on way to Christchurch, New Zealand. And in our summer, which is their winter, we do our observations from New Zealand. We are there usually for about 2 to 3 months in summer, and we do observations from New Zealand. So a question will be asked, why stratosphere? Why do we need to fly so high? And this two plot illustrated very well. What I'm showing here on the plot is on the x-axis, I have wavelength of light, and it's going from 1 micron to about 1000 micron. That's the infrared regime. On the y-axis, I have transmission, and the way you read transmission in this plot is if the transmission is 1, that means all the light that is out in the universe comes through our atmosphere and reaches the ground. So this plot, the top plot is for Mauna Kea. This is where the observatories are in Hawaii. And you'll notice that there are some regions in near infrared, near 1 micron, where all the light comes in. But as you go to longer wavelengths, say around 100 micron, the transmission is 0. Nothing comes in. So if you want to observe, say, any of the galaxies or any of star-forming region in 100 micron regime, you cannot do it from Mauna Kea because there is no light coming down to Earth. But because Sophia is a plane and it can fly up to 40,000 feet, at the 40,000 feet, the transmission profile of our atmosphere is completely different, because almost 99% of the water vapor that absorbs infrared radiation is below us, and there is just a little bit of water on top of it. There are other things that absorb infrared radiation. It's not just water. For example, this 19 micron feature, this is due to ozone. So ozone absorbs. So here again, even Sophia cannot observe. We'll have to, if you want to observe this thing, then you'll have to go to space, and that's where Spitzer observes these regions. So that's the reason we like to use Sophia with an infrared telescope to fly so high, so that we can, this whole wavelength range from 100 to 1000 micron opens up. Again, I don't think I need to tell about electromagnetic spectrum to this audience, but here is just so that we know what numbers are and what we are talking about. Here is visible wavelengths, which goes from 4 to 7 micron. You'll notice that I'm always talking about micrometer because I'm an infrared astronomer, and we always talk in terms of microns because that is the size of objects we are studying. Usually visible people who are doing optical astronomy, they'll talk in terms of angstroms or nanometers. People who do X-rays, they talk in terms of photon energies. But I, for this talk, will be always talking about micrometers. Infrared goes from about 0.7 to 300 micrometer, and submillimeter microwave and radio is above 300 micrometer. And to give these numbers are very small. So to give a handle on what this means, insert here is an image of a human hair. This white bar at the bottom is about 20 microns. So this human hair is about 40 microns wide. So those are the kind of, that is the kind of wavelength of light that we are looking at. It's the size of about the human hair. Again, this is another demonstration which I think you will appreciate. You all know this constellation of Orion. This is a visible image or optical image where you'll see the red giant Betelgeuse and blue giant Rigel. But when you look at the same part of the sky in infrared, it looks completely different. It looks something like this. So all the stars are disappeared now, and you see this fuzzy cloud-like structure. What is happening is that when you're looking at stars peak the most energy they throw out is in the visible part of the spectrum. So you are seeing it in visible light or optical light. But when in the near infrared and far infrared, the stars do not give a lot of radiation. So you don't see them in the infrared. Dust and gas, hot dust and hot gas radiate in the near infrared. So that's what you're seeing. I'll be using the terms gas and dust sort of interchangeably, but when I talk about gas, I'm mostly talking about atomic gas like hydrogen, oxygen, so on and so forth, or even like carbon monoxide. Whereas when I talk about dust, I'm talking about these extremely tiny particles of silicate and graphite. Those are the dust particles that are there in space. They are created in this gigantic molecular cloud like Orion, for instance. And those are those particles that coagulate and become larger and go into a star system and form disks. And from that disk, planets are born. So basically, we are all from, as they say, we are all starlight. We are all made up in space. So when I'm talking about dust, I'm not talking about large chunks like asteroids, but I'm talking about extremely small submicron size graphite and silicate grains. Here is again a demonstration of what's the difference between an optical and an infrared image. There is a landscape which you will see. There are valleys and mountains, so on and so forth. But when you look at in the infrared, then the warm-blooded animal pop up. So, oops, here it is. Sorry. There is the visible image, optical image, and then this is the infrared. So basically, Sophia looks at heat. It has heat vision, but we are not like Superman. We don't throw light from our telescope. We are more like Predator, where we see the warm-blooded animals, in this case, Army, glow up. Here are some of our instruments, Forecast, GREAT, and PPLS. Forecast is the instrument that I work most closely with, and the last one called HAWK Plus. Forecast is an imager and a spectrometer. So we can take images in the infrared going from 5 to about 30 micron, and it can also take spectrum of the same from 5 to 30 micron. On the other hand, HAWK is an imager and a polarimeter. So it can take images from 50 to 250 micron, but it can also measure the polarization of incoming light in the same wavelength regime. And the important part of that is if you can measure the polarization of light, then you can infer what the magnetic field is of the object you are studying. So this becomes very important. Later on, I'll be talking about one particular science case that I want to highlight today, which is a new research that happened a couple of months ago. And that's all about polarization, and we'll go into some little more details then. This is the last technical slide. So there is the resolving power of our instruments versus wavelength, and you'll see that we have a lot of different instruments sitting in it. It populates almost the entire phase space of resolving power versus wavelength. Just now, David also mentioned JWST, James Webb Space Telescope. It's also an infrared telescope, but it goes only from about 0.5 micron to 30, whereas for Sophia, we go all the way up to 1,000 microns. So James Webb Space Telescope will look at very faint and very far away objects, whereas instruments on Sophia, like XCs and Forecast, will look at the brighter objects. So there is a nice complementary going between Sophia and James Webb. Same thing with ALMA. ALMA is a radio telescope facility in Chile, and that merges very well with our instrument we call GREAT, which is a heterodyne instrument which looks at various elemental lines in these clouds or dust clouds that we study. So now I'm doing a transition from the technical part to a scientific part. Recently, Sophia was on the cover of, or not Sophia, but Sophia result was on the cover of Nature magazine, Nature Astronomy. And the title said Magnetic Field Properties in a Galactic Merger Remnant. So basically what they did was they studied Centaurus A. This study was led by my dear friend, Enrique Lopez Rodriguez. He used to be an instrument scientist with Sophia, but now he has moved to Kavli Institute of Particle Physics and Cosmology. And he has a huge program on Sofia to study galactic evolution using magnetic fields. And this was one of his first publication that came out from his legacy program. Most of you probably know about Centaurus A. It's a very complex and confusing system. It's a galaxy that is with the optical image looks something like this. It has this dark lanes which is filled with gas and dust, and you'll see that it's not like the usual spiral galaxy, even though it looks like somewhat, but it has this warped disk. So the gas and dust seem to follow on the edges, they are warped. So this source was discovered in 1826 by James Dunlop, who I believe was a Scottish astronomer working in Australia. The morphology of this galaxy is not well classified. It's not neither a regular like an elliptical galaxy, nor is it like a spiral galaxy. It's somewhere in between. The distance is not very well known again. It is between 10 and 15 million light years. Different distant measurements like Cepheid variables, supernovas, and planetary nebulas give different results. So we are not very sure the exact distance of this object, but it's about 10 to 15 light years away from us. This is a very famous object, and almost all the NASA's great observatories have observed this, including Spitzer, Chandra, Hubble, and now Sophia. But the first polarimetric observation of this source was done in 1960s, and it was done by Aina Elvis. She was a Swedish astronomer. She was working in Lowell Observatory in Flagstaff. I'd like to share this particular image because polarimetric measurements are inherently very difficult. It's when you're doing, say, a regular optical or infrared measurement, you put a filter, you take an image, and that's done. But for polarimetry, it doesn't work like that. We take polarizers in 4 different angles, and we have to take light, split the light into 2 components, take those 4 different angles, then merge them together to form an image like this. And these days, it is relatively straightforward because we have computers and all our instruments and the telescopes are automated. But when Aina was doing this work, everything was mechanical. Everything had to be done by hand. So she had to turn the filter wheel, get the polarizer in the right angle, put a photographic plate, take an image, remove it, turn the wheel again, take the next polarizing angle, put another photographic plate, take an image. So it took just long time to do these kind of work. But even with that simple thing, she got some very deep understanding of this source. So the way you read this image is that the background is image in the optical, but these lines that you see, this black and white lines, those are the polarization measurements. So basically the size of the lines tell us how much it is polarized. So if the line is this large, like on the top right here, that's about 5% of the light is polarized. So you will see that most of these are less than 5%. And the angle of the line tells what is the position angle of the polarizing, polarization measurement. So you'll notice that most of these lines seem to follow this dark line. So she concluded from that these are the magnetic field that we are seeing are from magnetically aligned dust grains. So the dust grains seem to be aligning with the magnetic field, and that's what we are observing. Just with these few observations, she concluded that. She also noticed that the shape was, in her paper, she said it is interesting, in quotes. She didn't tell what interesting was, but we'll see soon why she thought it was interesting. And she also noticed that since it was following the disk of the galaxy, then these magnetic field lines must be connected with the gas and must be pulled along with the gas. After that, there were quite a few other observations, all in the optical region of the electromagnetic spectrum, where they went bigger and bigger. They looked not just at the disk of the galaxy, but they started looking at other regions. Then in 1990s and 2000, with the advent of infrared telescopes and infrared polarimeter, remember in infrared we can look deep into the cloud, so we could look at the center of the galaxy. The center of Centaurus A is called an AGN, an active galactic nuclei. It is powered by a supermassive black hole that is sitting in the center. So the material from the disk, as it spirals in, falls in, but as it is conserving angular momentum, it will have jets that come out from the poles. I'll show some images later on where this will be much more clearer. But people started looking at infrared polarimeters measurements of center A, and they figured that in fact the center is very highly polarized. And again, they came to the same conclusion that Aina did, that these are all the magnetic field you are seeing is all dust grain that's aligned along the magnetic field in the disk or the torus of the AGN. Then, of course, came Spitzer, one of the best telescopes ever, I think, not just because I worked with it, but it really opened up our eyes to the infrared universe. The Spitzer was predecessor of JWST. It was a much smaller telescope, not as big as JWST. But in the infrared image in Spitzer at 8 micron, which mostly looks at PAHs, polyaromatic hydrocarbons, we saw this trapezium-like structure in the disk of the galaxy. The center bright thing you're seeing is where the black hole is sitting inside that. So it was a bit confusing to understand how this disk is warped or why it is warped in such a way. Is it even a disk, or is it a different morphology in there? But this next animation shows you how that disk forms. So here is, we are going into the galaxy. We are looking at Spitzer now. This changes into simulations where now we can turn it around and look face on, and there is your galaxy. That is the spiral galaxy that you are seeing when you look at this image, and that's why you see that parallelogram shape. Then, of course, we have Sophia, which is one of the most beautiful telescope, and Hawk instrument is one of the best one to do polarization measurement, because now we can do it at a very high resolution. So you'll see that all these lines, the spaghetti-like lines, are magnetic field lines that was measured using Hawk on Sophia. And once again, you notice that this warped disk, the magnetic field lines seem to be aligned along this warped disk, which you will see here. Of course, this image is a beautiful eye candy, and it is perfect for nature, but not for astronomers. Oh, before I forget, these are the X-ray jets that you're seeing on the top, coming from the north and the south of the galaxy. And the red things you're seeing are the dust particles. So as I was saying, this is great. This is good to look at. It's beautiful. But what astronomers do is we measure things. We want to know what exactly is going on. So here is what astronomer does. Excuse me. So the blue lines, blue contours, are the intensity of Hawk measurement at 89 micron. So we take a filter at 89 micron, let the light come in, and the brightness of it, that's what we have plotted. So it is pretty bright in the center, and as you go outside, it becomes fainter. These black lines are the magnetic field lines that we have measured. And for most part, you'll see that it does follow the intensity of the 89 micron emission, which is not surprising. But once you have this measurement, what Enrique and his team did was they tried to model this disk, like what physical condition need to be present in this disk to show us this kind of magnetic field. So they used two different models. One was a magnetic field that was spherical, that was along the disk, and if you look on the first image, panel A, that's what it shows. The other one was, because this disk is warped, they used a helical model of magnetic field to see the warp in it. And then once you have a model, you can look at it different angles. So the panel A looks at top down, whereas panel B looks edge on the entire galaxy. But then when you zoom in, you'll see that in the center, just like what Sophia shows, there is the grains are aligned and they go along the disk. But on the edges, there is changes. The angles start moving away from the disk. They go in different directions. So what does that teach us? That teaches us that in the optical, what we saw was true, that again, in the edge, they all align with the disk of the galaxy. That's where majority of the dust is. And then as we go outside, they start warping away. I have some echo, so if someone is on mic, please mute yourself. Thanks. So then once we have the model, you can compare your data to the model. So here in the black are the model that Enrique designed, and the blues are the measurements from Sofia. And to first glance, it looks like, yeah, they all seem to be following the field lines. That's perfectly fine. Their strength seems to be comparable to what the model is predicting. But there are some where the angle don't match. And if you plot a histogram of this, that is, if you take the model minus the measurement, and then you plot a histogram, what we call a residual, if you plot a histogram, if the model and your data is identical, then that histogram should peak at around 0. But as we know, our models are not always perfect. There is some discrepancy. So it's in this case, it's peaking at about 3 degrees. So it's close, but not perfect. The uncertainties in this measurement is about 5 degrees. But you will notice that this histogram is pretty broad. The width, the full width half max, the width of this histogram is about 27 degrees. So there is something going on inside in this galaxy that our model had not taken into account. So that's why it is broadening it. So it's telling us something fundamental about this galaxy, which just with looking at this model, we cannot understand. So we have to do something else. So we start looking at different phases of the galaxies. We look at the outer disk, the molecular disk, and the inner disk. And we plot on here in this
Lost audio.
Dr. Shenoy, we can't hear you anymore.
I think he has frozen, I think. Looks like his internet connection is dropped.
My wife has a problem where she'll be presenting and then her computer will lock up. She has to reboot when she's doing large Zoom meetings.
I think we'll just give him a moment and see if he can reconnect.
Sorry about those guys. Something happened. I just dropped, so I'm restarting it. Give me 1 second.
No problem.
Where was I? There.
I think we're all used to this at this point in the pandemic.
Let's see. I want this one. Share. Okay. So you see my slide again?
Yes.
Yes, you can see it.
Yeah, looks good.
Okay, thank you. So in the plot, what I'm plotting here is on my y-axis is the polarization intensity, polarized intensity, and on the y-axis is the regular 89 micron intensity. And you can see that we can differentiate depending on where these data falls into outer disk, molecular disk, and core. Outer disk is mostly made about gas. That is the black thing that you are seeing in the image here. The blue is the molecular disk. These are the regions where there's a lot of molecular gas like CO and dust like silicates and graphite. And the core is the real interior where the densities are very high. That's what we term as core of the galaxies. And as you can tell that at the core of the galaxy, the polarization intensity is pretty low. The polarization strength on the outer disk is about 15%, whereas the polarization in the core is about 1.5%. We can study the polarization with different tracers of gas and dust. So here I'm showing you three different tracers. One is the temperature of the dust, one is column density, and then the turbulent kinetic energy. Again, on the top panel, I have percentage polarization measured along the line of sight. Each of those dots are along the line of sight to the galaxy, each of those individual measurements. And I is the intensities. And as you see, as the temperature increases, the polarization sort of decreases. These two things we knew. Same thing with column density. We are measuring the hydrogen column density along the line of sight. And as the column density increases, the polarization decreases. This we knew. But this was new, the last part, the turbulent kinetic energy. This was measured using carbon monoxide from ALMA Observatory. And we found that the turbulent, as the turbulent kinetic energy really separates out, distinguishes between these three layers. So it's the turbulent kinetic energy that is sort of driving these polarization. So what does that mean? How do we think about it? So a cartoon way of doing it is, imagine the blue lines, that squiggly line you're seeing as the dust and gas in the galaxy, which is sort of turbulent, and the magnetic field are sort of connected to that. But our telescope, our instrument, has a footprint. It looks at a large region, and at the distance of Centaurus A, this region is about 100 kiloparsec. So it's looking at a large region. So we are not looking at individual measurements, but we are looking at averages. So when we measure magnetic field, we are measuring an average magnetic field in that beam. So if you look at a normal galaxy like NGC 1068, it all makes sense because, and this is the, again, Sofia image of Hawk image of 1068. The yellow line is our model for the spiral arm, but because most of the gas is flowing along the spiral arm, in the beam, our magnetic field kind of matches. So it matches with the spiral arms, which means that the magnetic field is now dominated by a large scale motions. Like the entire motion of the spiral arm is dragging the magnetic field along with it. But that's not the case in Centaurus A. In Centaurus A, because we saw such a high dispersion of 22 degrees, it looks like something is happening inside the beam of our telescope itself. So there is so much turbulence in there that the lines gets really squished, and the average magnetic field we measure in our beam differs from place to place. That's why you're seeing such a large dispersion. So a question would be, why are we seeing, even though it's like a spiral galaxy, why are we seeing this such a large dispersion, so much turbulence? And that is because of the evolution of Centaurus A. Remember, Centaurus A is a merger galaxy. It's a merger between an elliptical galaxy and a spiral galaxy. And after that merger, because the energy increased so much because of this merger, the spiral galaxy started moving faster, and the turbulence increased a lot. And we can see that in the plot above. The turbulence here is really high compared to normal galaxies, which would be down somewhere here. So those turbulent things inside the turbulent dynamos are the one that is sort of dominating the magnetic field. So what did we learn from this study? So the few thing is that the turbulent magnetic field is seen across the warp disk. That's the first image that I showed you. And this field seems to arise from small scale, not large scale, unlike normal galaxy like 1068. And this is mostly tied in to the fast rotation of the galaxy and the turbulent motion, kinetic energy of the gas itself. That concludes the science part of it, and I'm willing to take questions now. And when I'm taking question, I'll let the slide continue so that because Sophia has done so much observation, I didn't have time to go into each one of them. But I'll let the slides go, and if someone wants to ask me questions or whatever, that's perfectly fine. Okay, now we are open for questions.
Okay, very good. Thank you. Let me scroll up to the top. I actually have the first question for you. How does the cost of operating Sophia compare to the cost of operating an orbiting infrared observatory spacecraft?
That's a bit hard to answer. I mean, I know what is the cost of operating Sophia. So for our Sophia budget is about 80 million per year. But then the Sophia lifetime is longer, right? It's about 15 years, 15 to 20 years. Whereas most of the space-based observatory, their lifetime is shorter because of the cryogen. Lifetime is about 5 years. Like for Spitzer, it was 5 years. Then it was extended for 3 more years. But their base cost is expensive. So it's a bit hard to measure one-to-one. But I would say that I think the cost of running Chandra, Hubble, and Sophia should be in the same order, if that makes sense.
Well, and you have an advantage in that you can land it and do maintenance.
That's right. We can land and do maintenance. So some of the advantages of Airborne is, you're exactly right. We can land and do maintenance. We can change the instrument as and when we want. So for example, if a supernova shows up, if we know a little bit in advance, we can change the instrument, go look at it. We can go to any part of the world to do the observations. And last but not the least, all the new technologies, new instruments that are being developed that can be tested on Sophia before they are sent to space.
Oh, that's a huge advantage.
Unfortunately, we have not done a lot of that because there has been so much demand for the science returns that our advisory committee and our user committee always wants more data. So they're like, we are not done a huge amount of technology development, but we have the capacity to do it.
Oh, good. Ron Rannick asks, given the infrared wavelengths being observed with Sophia's 2.5 meter telescope, is any additional cooling of the mirrors and or instruments necessary?
Yes, definitely. Remember, we are looking at really when you look at these images, it looks so bright and it's like, oh, you can see this, but these are really faint objects. So most of our instruments are cooled using liquid nitrogen and liquid helium. So for example, Hawk instrument, it needs to be really cold, especially the Hawk detector needs to be really cold. So we first cool down the entire instrument using liquid nitrogen. Then we pump liquid helium and bring down the temperature of the chip to about, 0.16, 0.2 Kelvin. So about 160 millikelvins.
Wow, that's
and the mirror usually is not cooled, but because it is open to space and we are at 40,000 feet, it is cooled by the ambient temperature itself.
That's some pretty serious cooling.
For example, Hawk can fly we can observe continuously for about 8 hours. After that, we lose the coolant and then we have to land back.
I see. What is your maximum time airborne that you can do?
12 hours.
12 hours. That's pretty
Yeah,
long.
so we usually start in the evening around 6 or so,
Mhm.
depending on which instrument we have. If it is Hawk, then it's a bit shorter, but if it's forecast, then forecast doesn't need as the coolant requirement are not as stringent as Hawk.
Mhm.
So for forecast, we can start at 6.
Mhm.
It takes about an hour just to get up to the cruising altitude for us, which is 39,000 feet. And
Mhm.
then we can observe for about 10 hours or so, and then it'll take another hour for us to get down.
Mhm. Okay. Okay. That all makes sense. Good. Mark Chrisman asks, when the observing door is open, is there a transparent cover or is it open?
It's completely open. There is no transparent cover. Remember, we are looking at infrared, so you can't have, there has to be special material, like just the cover in front of our instrument is so difficult that the people who build this, they do one piece at a time for us. So having a cover which is 23 feet by 15 feet is just impossible. It'll be very expensive, and we don't want it because we just want the infrared light to come in.
Uh-huh.
So it's
Okay.
open to space.
Okay, good, good. Mehmet Ensoy asks, what are some of the interesting things Sophia has found?
Ooh, where do I start? uh, let's see. I'll just quickly go through this. So we have observed a supernova. This is a supernova that happened in 2016. We observed that and figured out what are the elements that were created in supernova. There was some planetary nebulas that we have seen. We have looked at the center of our galaxy. I'm not sure if I'm sharing this. Okay, there you go. That's better. So that's the supernova that we saw at the center of our galaxies.
Okay.
Sorry, not our galaxy, M82. We have seen stellar nurseries in W51. This was the first time we saw a large number of massive young stellar objects that was discovered in this particular survey. Um, Not many people have seen massive young stellar objects because they are so short-lived, they are hard to observe. This, I don't know if I can play this, but let's try. No, it's not working now. But this is a 3D measurement of carbon 2 line in the Orion cloud. So this is your classic Orion cloud, and these measurements were done. These were 2 million spectra were collected to make this image, and we can move this image to understand how the part of the cloud is blue shifted versus part of the cloud is red shifted. This is again the Orion cloud seen here, and this is the bubble that is here. Are all the bright thing you are seeing is O-type star, which puts a lot of energy and has blown a bubble across this molecular cloud. And different colors are basically different elements that are excited in this. What else do we have? Oh, this is a fantastic one. This is the center of our galaxy, the Milky Way. This was a forecast image. So this Y kind of shape that you are seeing is the material that is falling inside the black hole. So the black hole is sitting somewhere in the center. And we have an object called the circumnuclear ring, which goes around the black hole. And after this was done, we observed the same object using Hawk, and now we can measure the magnetic field of those streamers. So you'll see that the magnetic field are being dragged by the gas and dust that is falling into the black hole. So that's basically like channeling it going into the black hole. So yeah, we have done tons of these kind of work.
Thank you.
You're welcome.
Those are amazing images. Okay, let me scroll down. We had some issues with audio. Okay, Jorge Garcia would like to know are there any special coatings on the mirrors on the telescope?
Yes, there is, but I'm not an expert on it. There is a special coating that's for highly reflective infrared radiation. It's not the same one that we use on optical telescope. But to be honest, I'm an astronomer, not an engineer. As long as it works, I'm good. So yeah, but I can find out and send you the link to the technical details.
Okay, if you come across it, I'd be happy to forward that to him.
Okay.
That would be great. Let's see. I'm looking for more questions. Okay. Caitlin would like to know, is this kind of erratic turbulence seen in quasars or blazars?
I would imagine so. Uh, I It depends. It depends what the genesis of the turbulence is. How did the turbulence come about? If it is, but since quasars and blazars is this highly energetic thing, I think the center of those sources will have highly turbulent region, but the outer parts may not be. And the reason I'm not so sure about it is I don't know if there has been any polarization measurements done on quasars and blazars. They're pretty far and faint. And for Sofia, we still need bright objects to do these kind of work. Plus, because of the beam size of the Sofia, I don't know if we will resolve, like in Centauri, we can talk about outer region, the core, and the molecular region. Whereas in blazars, I don't think we can distinguish. So we'll need a bigger telescope. So,
Okay.
my when my kid grows up and he builds a 8-meter telescope in a Boeing 3000 Airbus, we will be all set. We can do quasars and blazars then.
A Boeing 3000 Airbus. I love that. Okay. Let's see. Bill Cast asks, are you able to change instrumentation mid-flight, or are you restricted to using a single instrument per flight?
No, we can't do that. These are massive instruments. They are you need an entire team of people to change it. And I mean, you guys have worked with instruments. When you fit your camera to a telescope or whatever, it has to be precisely fit, right? It's not. So imagine doing that, but on a much larger scale, like a scale of a plane. So no, it takes us about a good 2 full working days to change an instrument and make sure it is functioning properly. So we have to do it on the ground when the plane is in our hangar. We bring in the instrument, put it in, connect all the boards, and of course this is NASA, so everything has to be to specs, and there will be 3 QA people standing beside us, making sure the pressure on the nuts are perfect. So no, we can't do it on flight. We have to land.
Is this a
that's
hangar that's maintained to like clean room specifications?
If the instrument is open, then it has to be, because our detectors are very sensitive, so we don't want to open it anywhere. But our instrument itself are thermally and hermetically sealed, and there is a window through which the light comes in. That's the window that allows infrared rays to come in. So when we are in normal operations, it's fine because it is sitting by itself. But if you have to change something, electronic board died, or you have to change something, and when we open it up, then we have to do it in a clean room.
Okay, good to know. Good to know. Yeah, some of the airplane hangars I've been in have not exactly been very clean. July would like to know, who was your greatest mentor? Who is your favorite scientist and why?
Oh man, you are asking me to name names now. The first part is easy. My greatest mentor was actually it is 2 people, I think. One is my father. He because of family situation, he couldn't go to school. He didn't even graduate high school. But he was extremely intelligent, and he's one of the most well-known, well-read person I knew. And he always wanted his brothers and his son to study more. So he didn't care what I studied. Like when I was growing up in the Indian culture, it was all about being an engineer or a doctor. That's what Indians do. But I, like a fool, decided that I want to be a physicist and was going toward physics. And my dad was the one, when everyone opposed me, my dad was the one who stood behind me and said, yeah, I know you can do it. Go ahead and do it. Also, I was not a very good student because I wanted to have fun, not study. So I was most of the time not attending classes and stuff. So, but he always stood behind me. So he was my first mentor, I think, in younger days. But then when I joined AFA, Association of Friends of Astronomy, the president of the club was another gentleman named Percival Nerona. He has some Portuguese ancestry, who lived in Goa. He started the observatory, and he supported me a lot. Like in fact, today I'm here because of him, because he helped me when there were times when I was down and was ready to give up, especially coming to US to study astronomy. But he was the one who pushed and said, I think you can do it. So there were two or three, one professor in the university and my dad. So these were the guys who sort of pushed me to do these things. So they are my mentors. As for my favorite scientist, of course, that's me. No, I'm joking. As you know, I came from amateur astronomy background. So even though now I'm a professional astronomer, I think myself as an amateur. Like I'm not satisfied with studying one object. Like people will spend their entire life studying Centaurus A, and that is theirs. Whereas for me, it is like I want to study Centaurus A now because I'm working with this particular instrument. But then tomorrow, my mind will shift and say, I want to start looking at globular cluster. I want to see what's happening there. Then I want to go and see. So I'm on a paper which discovered water on Moon. So I want to go see. It has nothing to do with each other. So in nature, I'm an amateur astronomer, and which also means I like public talking and interacting with people. So my favorite scientist would be Carl Sagan, because he's the one who made astronomy accessible to everyone. He was like the superstar. He just went out there and taught people to appreciate what is it that is why are we so unique? Why is Earth so unique, and how beautiful it is out there? So I think Sagan would be my favorite scientist.
Aha. I like that. And very, very true. Let's see. David Schuldeis would like to know, how often do you fly?
Me personally, or the Sofia?
Mm-hmm.
Oh, me.
No, you personally.
Oh, me personally. So as I said, I work with two instruments, Forecast and Hawk. And most of the time when these instruments go online, we have a series of, I don't know, 2 weeks, between 2 and 4 weeks. And since there are multiple people supporting this, most of the time, if I go, I will fly for 2 weeks. That is 8 flights, 4 flights per week. So
Okay.
we fly Monday night to Thursday night. And sometimes we fly on Friday nights. But if I'm flying, then it'll be 4 times a week. And if I stay there for 2 weeks, that'll be about 8 flights back to back.
You're getting a lot of miles then.
I do get a lot of miles, but I always end up at the same place. I don't go anywhere.
True. Let's see. Jorge Garcia wants to know if you have any social media handles.
Yes, I should have mentioned that. Yes, we do have the usual YouTube channel. If you look for Sophia Telescope, you'll find it. YouTube channel. We have the Instagram, the Twitter. Just look for Sophia Telescope and you'll find it.
Okay. All right. Very good. Thank you for that. Michael Gardner asks, how long are your exposures?
depends. The one of the biggest thing for us is the infrared background, that just the sky glow and everything, and it changes on the time scale of seconds. So most of our exposures are really short. So when you talk about exposures, our exposure will be 5 seconds or 10-second exposure. But we keep doing it again and again so that we collect the photon, and our final exposure can be 3 minutes or 4 minutes or whatever. But individual exposures are very short. We also have a different technique of observing. It's not like optical astronomy where we look at the sky and take a picture. We have to do what we call chop and nod. So the secondary mirror on the telescope moves. So we can move our secondary mirror. So what? Let me see if I can show that here.
I liked the GIF you showed of the plane moving, but the instrument
telescope
pointing at the star and staying steady on the star. That was good.
So do you see this slide?
Yes.
Okay, so this red and blue squares are what we call the chop. That is where we are moving the secondary mirror, and that is in nod position A. So telescope is looking at one direction, and we get 2 images, and we subtract them to remove the sky. Then we move the telescope to the second nod position B, and then we chop the secondary again, which creates another pair of images, and we'll get an image where the sky is subtracted. Once we get that, we subtract these 2 things so that we remove all the contribution from the telescope itself and then get the final image, if that makes sense. So these are not the observation, the normal optical observation. You have to remove the background from the sky, and you have to remove the background from the telescope itself, because everything is warm relative to the light that is coming in, if that makes sense.
Okay, very good. Yes. Greg Fogarty says, fascinating presentation. Thank you. I'm curious, do you have to pay for your carry-ons?
Thankfully, no, but my carry-on when I go is a backpack with my laptop and a sandwich. So we don't have luggage there. But no, we don't have to pay for our carry-on.
And you don't have flight attendants either, it sounds like.
We don't have flight. For the longest time, we didn't even have a coffee maker in the plane. So it was hard. Observing a whole night without coffee, I can't survive. Finally, they did bring coffee makers, and now we do get coffee, except if you're on the great flight. The great instrument is a heterodyne instrument, and it is in sub-millimeter range. So you cannot run your microwaves or coffee machines, because that will interfere with our observations. So on the great flight, there is no microwave and there is no coffee machine.
Oh my goodness. Wow, that's tough duty. Do you fly out of the same airport all the time when you're flying out of North America?
It's NASA's Armstrong Flight Research Center in Palmdale. That's where the plane is based. It's close to Edwards Air Force Base, so we go out of there and land next day morning.
Oh, that's nice. I've been to Edwards. It's a fascinating place. Yeah. All right. Does anybody else have any more questions? Well, I want to thank you, Sachin. This has been a very informative talk, very interesting, and we're delighted to have had you here, and we'll probably ask you to come back another time. Yes, everybody.
Oh, I'd love to. Just let me know what you want to. Maybe we can talk more about science or whatever. Just let me know what you want to know about, and I would love to talk. I would also love to come and meet you guys once you guys start going out and doing your things.
Oh, absolutely. Well,
I'd love to come to your star party or one of those things and hang out with you.
I'll find a way to add you to our email distribution list if you don't mind getting all of our announcements.
Perfect. That would be really nice.
Okay. All right. Very good. I'll make that happen. Well, we appreciate that.
I'm just putting in my my personal email here, so you can contact me at that if you just want to add that to your list or whatever. I would really appreciate that. Thank you.
Okay, good. Let me copy that and put it into a document here somewhere. So
I can email you later too. That's fine.
Oh, trust me, I have something open all the time that I'm always working on. Yeah.
Let me see. Thanks, Ron. Thanks, Kathleen. Appreciate it. Glad you
Thank
liked
you,
it.
Sachin. Thank you so much. I'm glad I met you at the DMNS. I don't know if that was 2 years ago, 3 years ago at the space
Yeah,
day.
I think now